All right, so omega naught is equal to 0. T is 20 seconds. And I want to know what is its angular acceleration. That's alpha. I also know that it moves up to an angular speed of 10 revolutions per second, so that's omega is 10 revolutions per second. Now you could convert that to radians per second, but I'm going to leave it at 10 revolutions per second because my units down here are all in revolutions per second squared. So I have omega equals omega naught plus alpha t. I'm looking for alpha. Subtract omega naught from both sides, divide by t, and I can find my angular acceleration. That's going to be 10 minus 0. Divided by t, which is 20 seconds. 10 over 20. So A is the right answer here, 0.5 revolutions per second squared. Again, if you're ever uncertain about your units, just convert them to radians and then convert back to whatever the units are. Be careful though, watch your units on the test, okay, to make sure that everything's on the up and up. Since we are dealing with these 3 different units for our angles. Just check your units in the problem, check your units in the answer. All right? Let's go down here, see what else we got. Let's finish up the clicker questions from last time. Where did we leave off? I'm sorry, Maddie. This one? Okay. Oh, shoot. I don't even want to get into this one. Is that okay? I'm going to skip this one. And you can just put an X to it. All right, I'm going to go through it real fast so you don't see the answer. Okay, don't worry about it. It's not a big deal. Okay, a rigid object is rotating with an angular speed that's less than 0. It's negative. The angular velocity vector, omega, and the angular acceleration are anti-parallel. That's a fancy word for in the opposite direction. The angular speed of the rigid object is doing what? So the velocity and the acceleration are in opposite directions. The speed is negative. So what is the object doing in its rotation? All right. I'll stop at 115. 115. Okay, B is the right answer. It's clockwise. I know it's clockwise because it's negative, and it is the acceleration. What was it? Was it B? Yeah, the acceleration and the velocity are opposite directions. That means it's going to be slowing down. All right, so it's clockwise and it's decreasing in speed. So B is the right answer. Okay. Oh, that's the end. Yeah. Okay. Yeah, I did pretty well on that one. Do you hear about? Shoot, how's it go? Do you know why Tigger stuck his head in the toilet? This is like a 4th grade boys joke. Okay. You know why? He was looking for poop. No, anyway.
Can you go over the two from what we just did?
The one I skipped over?
Like, because you gave us the answer, but you didn't really tell us how to do it.
Oh. This one? Oh, okay. Yeah, so I'm looking at 5 revolutions per second. So I have 5 revolutions per second. I want to express it in radians per second. So I say 1 revolution is equal to 2 pi radians. My revolutions cancel, and I'm left with 5 times 2 pi. That's equal to 31 radians per second. Okay? All right. So that's all of Chapter 7. We're going to see more of Chapter 7 in Chapter 8, because Chapter 8 is really sort of bringing everything together. So you'll see a lot more rotation on the next exam. But yeah, this is all Chapter 7. In fact, Quiz 4 goes down through Chapter 7 in the back of your book, up to number 8. Okay? So the test will be 5, 6, and 7. You know, Chapter 5, we did a little bit in the first part, so you won't see any calculations of work. But work still comes up a little bit, because we had the work energy theorem and stuff like that. But you won't have any of those questions like, is this work positive or negative, or guy has a force and pushes on an object at a certain angle. None of that, because we had all that last exam. But you will see conservation of energy. You'll see conservation of energy, of course. You'll see work energy theorem. I do work on an object. How do I change its energy? You'll see elastic potential energy. Can we write this down?
Yes.
Okay. We're having a help session on Tuesday, but we'll spend a little bit of time just sort of summarizing the test. You should have a blank page on 182 if you want to use that. So with Chapter 5, we'll cover this again at the help session, and I'll hand out the exam at the help session just for you to look at, and then I'll take it back up. But right, that's what I do every week, right, on Thursdays? Yeah. All right, so Chapter 5, we'll have conservation of energy. That means, you know, listen, you're going to have one of these roller coaster type problems where I'm asking you what is the energy at particular points, or what is the speed at a particular point, or what is the height at a particular point. So make sure that you're up on that. They're on every test. It shouldn't be a surprise to you. But you will have one of those where you ask, what type of energy does it have at particular points? So I have potential energy, kinetic energy. I only have kinetic energy down at the bottom because H is equal to 0. I have potential energy and kinetic energy here. And then when it comes up and comes to a rest, I only have potential energy. So make sure that you can do that. You'll have a couple problems that are based on a scenario like that. Make sure you can do that. You also have work energy theorem. Work causes a change in energy. So if I do work on an object, I change its energy. So for example, if I have a force that acts over a certain distance, that causes you to change the energy of that object. All right, so be able to calculate then how much does it change the energy, or how much work do you need to do to take away an object's energy. And that's all based on this work energy theorem. The work is force times displacement, and usually we're talking about kinetic energy. You sort of have to let the context of the problem rule it. Whether this object is changing its position in terms of the Earth's gravitational field, that would mean gravitational potential energy. Or is it changing the object's speed, which is usually the case when it would look like this, that our work causes a change in kinetic energy. So conservation of energy, work energy theorem, we have elastic energy. Elastic energy also wrapped up in this is Hooke's law, F is equal to negative kx. So if I compress a spring or stretch a spring, I get a force that's described by a spring constant k. That's on your equation sheet, I think. You will have your equation sheet. I'll print it out and give it to you. But you want to look at it, make sure that you're familiar with everything that's on there. Question?
Kx squared.
No, that's for elastic potential energy. She asked if it's kx squared. No, this is for the force, which is just kx.
We had some like on the homework and stuff like this.
I'll have to show you that, yeah. Mm-hmm. Jocelyn?
Well, I'm just being that negative or it should just show direction.
Yeah, the negative just shows direction. Often on those, I usually just ask the magnitude. All right. So this is Hooke's law. I'm sorry. Yeah. So this is for the force. This isn't energy. All right. Now the elastic potential energy, however, you're right, is 1/2 kx squared. And we have similar problems that we had with the gravitational potential energy. We worked through some problems like this. Like, for example, I have this spring. I have a mass on the spring. If this is the equilibrium position, and I stretch it out to a distance x, I don't know, xs or whatever, what is the speed when it goes through the equilibrium position? It's just like the gravitational potential energy problems, except you're now dealing with a 1/2 kx squared instead of a mgh. So out here, if the speed is equal to 0, the energy is all in potential energy, which is 1/2 kx squared. And here, there is no potential energy because x equals 0. The energy is all in kinetic energy, 1/2 mv squared. So you would set these two equal and solve for the speed or whatever it is that you're looking for. The speed, like in this scenario. All right, so that's, I think that's all of chapter 5. Let me just double check. Oh, you need to know conservative forces, what conservative forces are, how they act. Conservative forces, they conserve energy. A second. Also, conservative forces are path independent. That means it doesn't matter the path that you take, the amount of work that force does, it's path independent. Remember the mountain problem, you go straight up or you take a windy road, you still have the same gravitational potential energy. That's because gravitational force is a conservative force. Conservative forces conserve energy. Conservative forces are path independent. Conservative forces are field forces, right? And non-conservative forces do not conserve energy, are not path dependent, they're path independent. I'm sorry, did I get that mixed up in my head? I'm sorry. Non-conservative forces like friction are path dependent. Conservative forces are path what? Independent. And just a second, and a good example of a non-conservative force is friction. All contact forces, really, most contact forces are non-conservative. Justin?
So normal force is considered conservative?
A what force?
A normal force. Because it's always on the general area.
A normal force is...
Yeah.
Yeah, a normal force is, you could consider it as a non-conservative force. Doesn't have to be, though. But the way we've been talking about it, yeah, we'll consider it as a non-conservative. Okay, just think, only field forces are conservative. Okay? All right. Elastic potential energy, power. Power is energy over time. Know the units, watts. It's a joule per second. Not even, I don't even remember if there was anything for that. Okay. Then chapter 6 with momentum. Momentum, we had sort of two classes of problems, and then you need to sort of understand the idea of momentum, the different collisions, elastic and inelastic. So with chapter 6, we have conservation momentum. That is that the initial momentum equals the final momentum. You'll know these problems because they involve collisions and they involve two particles that are moving around. These will be different from the impulse problems You'll know the impulse problems because they involve forces. Impulse is F over delta equals delta P over delta T. This is like the truck running into the wall, those sorts of problems. Or you have one object that's running into a stationary thing, like a wall or a tree or something like that. And I'll ask you questions about the forces. All right? So I have the conservation of momentum, where I have collisions of two particles, and then impulse problems. Those are your two big classes. You'll have one or two of those. I think you have a couple problems for conservation of momentum and just one problem for this. And then also, you need to know the different collisions. We have elastic and inelastic. Elastic collisions conserve energy. And momentum. And inelastic collisions only conserve momentum. They do not conserve energy. Elastic collisions are like the collisions between gas particles, for example. Anytime you have objects that don't touch when they collide, charged particles, well, there aren't many elastic collisions, but anytime they don't touch, because when they touch, they lose energy. And then inelastic collisions are everything else. And then chapter 7. Chapter 7, you need to know your directions of your angular displacement. Positive is counterclockwise, clockwise is negative. So your definitions of angular displacement. Your angular quantities, I'll call it that. All sorts of things wrapped up in this. The sign of displacement, positive or negative. Positive is counterclockwise. Negative is clockwise. You need to know your unit circle, or at least know how to convert between different measurements of angle. You need to know how to use your kinematics equations. Again, they're a lot like the ones that we worked before. Not multi-step problems, usually just a simple one-step problem. Really just reading the problem and figuring out the quantities that you want to use and then plugging them into the right equation. You have those equations, but you need to know what the variables mean and how to apply them. Kinematics equations and centripetal force. I think that's it. Yep. And centripetal forces. Like some of the examples we've worked, like with the frictional force, the car going around the curve, the tension in the string, those sorts of things. Look at the homework as well. There's some good homework problems on centripetal forces. Questions, y'all? What time is it? I'm not going to let you out, I'm sorry. I know that y'all want to get out. But questions? I'll move on to the next chapter. I know y'all hate that, don't you? Let's smile because it's a happy day, okay? Listen, my wife and I, like, we have this pact. Because I used to let students out because I would get tired. Like, I'm really tired right now. And I would say if I was tired, it's like I'd let the students out right now. But that's very bad practice. Like, you don't ever want to do that because y'all are missing out, right? You pay good money to be here. So it's like now we have this pact. It's like we shall never let our class out early. And we hold one another accountable to it. Okay? Okay? What, Allie? We can do. Do y'all want to do some practice?
Yes.
Okay. No, we can do that. Y'all want to look at some old exams?
Yeah.
Okay. Let's try to get one we haven't done before. All right, this is a good one. let's do this one. This one picks up with Chapter 7. Chapter 7 is sort of what we spent the least time on, so let's start with that. A tire is mounted on a balancing machine. It's initially at rest. It begins to rotate. In 5 seconds, the tire moves through 3 revolutions. In radians per second squared, what is its angular acceleration? So you look at this, and the first thing you want to see is that the units are sort of mixed up, right? So you need to, yeah, Jane? Oh, this is Fall 06, Exam 3. So the first thing you want to notice is that your units are a little mixed up. And so my answers are given in radians per second squared, but I have this displacement in revolution. So I want to convert that into radians. So that's going to be my angle theta. It's 3 revolutions. 1 revolution is 2 pi radians. That's 6 pi radians. That's my angle theta. And let's see what else I have here. After that, it's initially at rest. That's my omega naught. I have the time here, which is 5 seconds. And I want to know the angular acceleration. What do we call that? That's my alpha, right. So I know omega naught equals 0. I know that t is equal to 5 seconds. And I want to know what is, not omega, I want to know what is alpha. So, well, I can use this equation of my kinematics equations. I know omega naught is 0, so this whole term goes away because omega naught equals 0. And then I solve it for alpha. Alpha then, multiply both sides by 2. It gets rid of that half. Divide both sides by t squared. So alpha is 2 theta over t squared. That's 2 times 6 pi divided by t squared, which is 5 seconds squared. That's 12 pi. That's about 36 over 25. Is B the right answer? Yeah, so it's 1.5. That's a good example of what you could see on Wednesday. Number 2 is also a good example. You will have a conversion problem. It may be a displacement, it may be a velocity. But it has a merry-go-round that goes through 3.5 revolutions. What is that in degrees? Can y'all see this in the back, by the way? Zach? Y'all can't see it? Zach can see it, but no way else. Okay, I'll zoom in a little bit, sorry. Let me clear this. Is that better? Is that better? Okay, good. Okay, merry-go-round goes through 3.5 resolutions. What is the angular displacement in units of degrees? Okay, so I know that in 1 revolution there are 360 degrees, so I'm looking at somewhere around 1,000-ish. Yeah, so A must be the right answer, right? I would say 3.5 times 360 would give me the right answer. Number 3. Oh, this is a good one too. I should have just given y'all this test. What's that? Oh, no, I've already printed it and stuff. All right, a ball. I would have it. Shoot. A ball has a mass of 1 kilogram and is swirled in a circle. The circular path has a radius of 3 meters, moves at constant velocity. In 2.5 seconds, the ball moves through an angular displacement of 12 radians. What is the tension in the string? Okay, so the tension in the string, that's going to key me off, and I'm looking for what? The centripetal force, because the tension is the centripetal force, right? So that's going to key me off that I'm looking for this tension, which is the centripetal force. But I'm missing some stuff. Like I have the mass right here, and I have the radius, but I don't have the velocity. However, I do know that in 2.5 seconds, it goes through this angle theta. So omega is equal to theta divided by t. Now this comes about from one of your kinematics equations. Theta equals omega naught t plus 1/2 alpha t squared, but alpha is 0, so that goes away. So omega equals theta divided by t. But it's just a general idea that this velocity is distance over time, or angular distance over time. So my omega is theta over t. That's 12 over 2.5. What is that? What is it? 4.8? Okay, so that's equal to 4.8. But be careful, because this isn't my linear velocity, v. This is omega. So I need to either calculate v is omega r, or do this m omega squared r thing. Either one you want to do is fine. I'm going to do it this way. So that's the mass, which is 1 kilogram, times omega squared, which is 4.8 radians per second squared, times r, which is 3 meters. So that's 1 times basically 5 squared times 3. It should be right around 75. B must be the right answer, right? C is the right answer? Okay, I guess I was wrong. All right, so C is the right answer. Okay? You want to look at some others from other chapters? All right, let's go back. Follow 6, but we'll go back to the previous test. This was exam 3, but let's look at exam 2. You'll have one of these, of course, so make sure that you can do this. Have a bead of mass of 0.1 kilograms, its rest of 0.8, it goes down the slope. What is its velocity? So how would I do this? I would look at my energy. Initially, it has what type of energy? Only potential? Does it have kinetic initially? Are you sure? It doesn't have any kinetic because it's not moving initially. It only has potential. Because it says the bead has a mass and is at rest at point A, so it has no kinetic. It goes down the slope. At point B, it only has what type? Only kinetic. So I'd set the potential energy at the top equal to the kinetic energy at the bottom. You just want to be able to look at these and figure out, okay, here I only have potential. I only have potential because V is equal to 0. And down here, H is equal to 0, so I only have kinetic. So I set my potential energy at point A equal to my kinetic energy at point B. So the potential energy is mgh. It's 0.1 kilograms. I think I used 9.8 here. I'm going to use 10 times h, which is 5 meters, equals 1/2 of 0.1 kilograms times v squared. All right, the 0.1s cancel out. I get 50 divided by 1/2 equals v squared. That's 100. V is equal to 10. Or it was 9 point. It was A actually. I used 9.8 there instead of 10. Okay. Yeah.
So when you're saying that C, the bead's still moving, would it have potential and kinetic?
It would have potential and kinetic, and you could have a problem like that. So in this one, if we were instead looking at point C, we would say the potential energy at point A is equal to the potential energy at point C plus the kinetic energy at point C. And then you would solve then for the velocity at point C. Be careful with your positions, because note the positions are different. I would have mg times 5 equals mg times 2 plus 1/2 mv squared. Yeah, Jocelyn. Why, what now? They're assumed to be equal because you only have conservative forces. And when conservative forces act, they conserve energy. That means they don't lose energy. Whereas non-conservative forces do lose energy, like friction or what have you. Oh, look. It's 11:40. Is that when we get out, 11:40? It's almost 11. Okay. You have a good day, okay?